Let's start the session, sir.
Yeah, thank you. Good evening, dear students. We are going to start the session, and today we are going to see what is about the time complexity and how to find out the time and space complexity of algorithms. And just I'm sharing my whiteboard to you. So we have seen yesterday what is the space complexity, and now we are going to see the things regarding the time complexity, as well as we are going to solve the things regarding the time and space complexity of different algorithms. And the time complexity is the amount of total time needed to execute an algorithm to run to its completion. So actually, total time is a combination of two things. So that is nothing but compilation time as well as execution time or runtime, whatever it is. So compilation time. So this compilation time, as all of us know about this one, once the algorithm, which is in the form of a program, is successfully compiled, no need to compile once again. That's why, so successfully compiled program, no need to compile once again. So here the time complexity majorly focusing on execution time. So in order to find out the execution time of algorithm, which is in the form of a program, so we have the analysis like a posterior analysis and priori analysis. So our focus is on a priori analysis. So there we are having the concept of finding out the time complexity with the help of a step count, total step count. Right. So there are non-recursive algorithms are there and recursive algorithms are there. So we are going to find out the time complexity with the help of total step count. So this is the concept. And one more thing, we are going to solve the algorithms, a recursive algorithm especially. So these are the very, very important algorithms. We are going to solve the problems with the help of a recurrence relation. We are going to form a recurrence relation and resolve that recurrence relation based on the given problem. And as we know that the thing is time complexity is focusing on the number of statements within the algorithm and how many number of times each and every statement is going to be executed. So for example, if I take algorithm, the simple algorithm that I am taking here, a comma n. So s is equal to 0.0. For I is equal to 1 to n, do s is equal to s plus a of I. Written sum or written s, whatever it is. So this is the simple algorithm. It's a non-recursive algorithm. Yesterday we have seen how to find out the space complexity for this one. And today we are going to see the time complexity for this one. So this is a algorithm heading and this is the body part. And here we are going to focus on the number of statements, steps for execution, whatever. Yes, steps for execution. And frequency, the number of times it is going to be executed. And total steps. So these are the three columns we need to consider. Oh, sorry. Steps for execution, frequency, and total steps. These are the things need to be considered now. So here, how many statements are there? One statement. How many times it is going to execute it? It is going to execute it for one time. So whereas this statement, first statement, for I is equal to 1 to n. So how many times it is going to be executed before of that one? So how many steps here? How many statements here? This is one only. So steps for execution is one, and how many number of times it is going to be executed, right? So we can write this one in the program code like something like for I is equal to 1, I less than or equal to n, I plus plus. Okay, so this is the statement. So if you consider this for loop, how many number of times it is going to be executed? So it starts with 1, and all the time it is incrementing till it reaches the I less than or equal to n. This is the test condition that we are having. So 1, 2, so on. It is going to be incremented, and finally it come to the one stage that it is this condition is not, this condition is going to be not going to be satisfied. In the sense, for example, if I say that n is equal to 5, so I is equal to 1, so I is equal to 2, I is equal to 3, I is equal to 4, I is equal to 5, like that incrementing is going to be taken place. So whenever the text condition is saying that 5 less than or equal to 5, yes, it is again it is satisfied, and again I will be incremented. So and now it is going to come again and check that whether it is satisfied or not. So here it is not going to be satisfied. Then we will come out of this for loop. So finally, what we are going to say about this for loop, how many number of times I gets incremented. So if it is n is equal to 5, it's from 1 to 5 plus 1, that is 6. So the frequency of this for loop we are going to consider for n plus 1 number of times. So how many steps here? One step only. And how many number of times it is going to be executed? It is under the influence of this for, it is going to executed for n times. So what about this statement, the return statement? This is 1, and the frequency is only for one time. So steps for execution, frequency. So this is a 1 into 1, 1 into n plus 1, 1 into n, 1. So total it is a 2n plus 3. So that is the total step count for this one. Total step count is equal to 2n plus 3. So what is the highest degree over here? It's a n power 1. So it is in the form of order of n that we are going to see that this is a big O notation. Usually time complexities and space complexities, by default, we are going to represent with the help of a notation that is a big O notation. We are going to see the asymptotic notations, the big O notation, theta notation, omega notation, and small o and small omega, small theta, all the notations we are going to see one after another. But here the step count, it is conveying that it is 2n plus 3. So by taking the step count, we are going to understand the algorithm is going to execute it for having the multiple number of instructions, each and every instruction, and the frequency of the instruction, and total number of steps it is going to consider. And finally, it is in the form of a 2n plus 3, a polynomial or an expression, whatever it is. So it is a order of n. So that is the thing regarding the finding out the step count, total step count of the given algorithm. And coming to that, if I take an algorithm like this, I'm going to add two matrices A, B, and the resultant matrix is going to store into matrix C. The for loop for I is equal to 1 to m do. And again for j is equal to 1 to n do. And here C of ij is equal to A of ij plus B of ij. So this is simple addition of two matrices. So we have considered the double dimensional. Yeah, thank you. So this is a algorithm addition of two matrices, like the double dimensional arrays we have considered ABC, and the order is mentioned as m by n. So I runs from 1 to m, j runs from 1 to n, Cij is equal to A of ij plus B of ij. So now we are going to find out the step count. So from there we are going to find out the time complexity. So step count when you are trying for this one, so we have to consider that one, steps for execution and the frequency and total count. So now how many number of steps are there? There is this one. How many number of times it is going to be gets executed? Frequency it is asking. So 1 to m it has to run, and there is a text case. So whenever it is executed, is a m plus 1 time it is going to be now considered, and whenever it is m plus 1, we are going to come out of this for loop. That means frequency of this for loop is m plus 1. Whereas coming to that next statement, this is a single statement. And again, how many number of times it is going to be executed? How many number of times the frequency is going to be mentioned for this one? It is running for 1 to n. Actually, whenever it is coming from 1 to n, so it is n plus 1. So this is 1 to m. That's why we mentioned this one m plus 1. We know that why it is a m plus 1 in the previous example too. And this for loop is under the influence of this for loop. So we can also mention like this. So whatever within the brackets of this one is going to be executed for m times. This for loop is going to execute for m plus 1 times. So this for loop is going to be executed for n plus 1 time into this m. And coming to the innermost statement, that is a Cij is equal to Aij plus Bij. So this is a single statement itself. So how many number of times it is going to executed, right? So it is going to execute it for, so this is under the influence of this n, this for loop j is equal to 1 to n. This for loop is under the influence of this for loop I is equal to 1 to n. So totally it is going to execute it for m into n times. So that is the thing regarding the frequency. So the total it is mentioning 1 into m plus 1, 1 into m into n plus 1, 1 into m into n. So finally what we can say about this one is, yes, 2mn 2m plus 1. This is the total step count. 2mn plus 2m plus 1. So by looking this one, we can understand that. So this is a order 1 to m by n. For example, if m is equal to n, then automatically it becomes, just I'm writing here, if m is equal to n, 2n square plus 2n plus 1. That is the step count, right? So what is the higher degree term here? 2n square is the higher degree term. So we are going to consider this one highest degree n square. So n square plus something, this is a constant order of n square. So usually like this, we are going to find out the time complexity from this step count. In the similar way, let us consider that algorithm. It's a non-recursive algorithm. It here we are mentioning f of n is equal n less than or equal to 1, then write n, else so we have the two numbers that we consider. fnm2 is equal to 0, fnm1 is equal to 1. Usually it is 0, it is 1, but we can take it in any manner, no issues. So here I is equal to 2 to n do. Fn is equal to 1 plus fnm2. And fnm2 is equal to fnm1. fnm1 is equal to fn. And writing the value of fn. So this is the algorithm. So our focus is finding out the step count for this non-recursive algorithm. Right. So if you are taking this into the consideration, right, we have the things like if n is n less than or equal to 1, then write n. So that means if n is equal to 0, so automatically if it is gets considered if n is equal to 0, what will be the step count? So the comparison the comparison condition followed by the displaying this. So there are two things that we have to consider. And if at all, if we consider that if n greater than 1, right? So the remaining part that we are going to consider now, the remaining part. So this is the remaining part. And here, the previously as we followed like that, say similar way, we are going to follow it. Steps for execution. How many number of steps are there? Here, 2 steps are there. How many number of times it is going to get executed? It's single time. So how many number of times this for loop is going to, how many number of steps are there? This is 1. And how many number of times it goes? It runs, it starts with 2 and it goes on up to n. Actually, it goes on up to n plus 1. So 2 to n plus 1, it is nothing but n. So coming to the statement here. So what is the statement here? This statement, how many number of times it is going to execute it? sorry, steps for execution is 1. Number of times it is going to execute it is, this is under the influence of this for loop. This here we mentioned that this is n. Obviously, inside the brackets, obviously it is n minus 1. And coming to this, here the combination of two statements, right? So that's why it is a two steps. And how many number of times? Again the same, n minus 1. And finally, this is 1 and frequency is for 1 time. So it is a finding out the value of the nth Fibonacci number. So total step count we are supposed to find out. So this is a 2 into 1 to n. This is n minus 1. And this is 2n minus 2. And this is 2. So if you add all these things together, you're going to get 4n plus 1. 4n plus 1. So total step count for this algorithm is 4n plus 1. So it is in the form of, again, so higher degree term is n power 1. So it is something like we're going to consider that with a constant into some n. So we are going to consider this part in the order of n. So that's the thing regarding the finding out the step count for the algorithm, non-recursive algorithm, that is shown there. And coming to that, and if I take algorithm, one more algorithm, there is a factorial. Let me say factor of n. So here initializing with 1, for loop I is equal to 1 to n, do. And here the fact is equal to fact star I. And finally, we are returning the value of that. Now, let us consider the same thing once again. Steps for execution, frequency, and total. So here, how many number of steps? One step. How many times? For one time. One step, how many number of times? So it is n plus 1 number of times. The one step, this is under the influence of this for loop, and it will be executed for n times. And finally, this one step, it is going to be executed for one time. So here the thing is, total is 1 into 1. This is n plus 1. 1 into n plus 1. This is 1 into n, and this is 1 into 1. That is 1. So we find the total of this one. This is a 2n plus 3. So total step count for this one is 2n plus 3. So higher order degree is at again the 2n only, power 1. So 2n plus something is there, but we are going to consider that one as the higher degree term only, that is order of n. Likewise, we are going to find out the step count for each and every non-recursive algorithm. And finally, we are going to derive solution in the form of a, either it may be a logarithmically bounded or polynomially bounded or exponentially bounded, whatever it is. So here, big O of n, we are representing this one. So this is the time complexity. Fine. And whenever we are coming to the recursive functions or recursive algorithms, so how we are going to deal this area, that is also one of the focusing areas in GATE examination. So algorithm, my name of the algorithm is A, parameter is n. Here the condition is if n greater than 2, then written a of square root of n, else written 1. So it seems to be a very simple and it's a very tiny algorithm, but actually it is very interesting. And IIT Kharagpur asked this question once, is asking about solve this algorithm and find out the time complexity for this algorithm. So it is in the form of a recursion only, the n and square root of n. So whenever n greater than 2, then it is a of square root of n. So here we are supposed to find out the recurrence relation for this one. So definitely we can write recurrence relation. So there are two cases that we can consider: n is greater than 2 or less than or equal to 2. For example, if I take that t of n is equal to t of square root of n plus 1. So what is the condition over here? N greater than 2. So whenever this gets satisfied, so it is going to be invoked or called, return a of square root of n. So or else it is mentioning something like return 1, n less than or equal to 2. So here the condition gets executed, then it is coming to this one, right? That's why t of square root of n plus 1. So here the thing is, we have how many number of times that the thing is going to executed when you are performing the operation. So here the operation is no, we are checking here the condition. So whenever that kind of condition gets satisfied, then it is coming here. That's why. So it is in terms of t of n is equal to t of square root of n plus 1. So the comparison that we performed out there. Now we are going to solve this recurrence relation. So though it is simple, but it is we have to pay much attention to solve this problem. Okay. Now by looking this, it is not that much easy to solve the problem like the simple problems. If at all our recurrence relation is t of n is equal to t of n minus 1, like this, by repetitive substitution we can able to solve this one, right? Let us consider this first simple recurrence relation, and how to solve this one we can do it, right? This recurrence relation for many algorithms also there, but this before going to that, t of n is equal to t of square root of n plus 1. So we are going to solve this one first. So here we can say that t of n is equal to t of n minus 1 plus 1, and in the place of n we are going to substitute n minus 1. So how it will be? So t of n minus 2 plus 2. So from this step only we could get this like this. Next one is t of n minus 3 plus 3. Next one is t of n minus 4 plus 4. So on. T of n minus k plus k. Likewise, it is going to be repetitively substituted in order to find out the time complex t from this recurrence relation. So finally it became t of n minus k plus k. So if I'm taking that, if n is equal to k, right, then obviously it becomes t of 0 plus n. So t of 0, it may be a constant like 1 or 2 or 3 or 10 or 20, whatever it is. This is a constant. So this is c plus n. So what is the higher order, higher degree term over there? This is n. So that's why we can say that this is order of n. So like this, we can solve these kind of no recurrence relations. So t of n is equal to t of n minus 1 plus 1. T of n is equal to t of n by 2 plus n. Like that, the repetitive substitution method, we can solve this one. And we are coming to that this kind of recurrence relationship, how we are going to solve it. So now t of n is equal to t of square root of n plus 1. That is the recurrence relation here. So we can take that if n is equal to 2 power k, because it is a square root is there. So I can show it something like 2 power k t of 2 power k by 2 plus 1. Because it is no square root of n, square root of 2 power k, the 2 power k by 2. We mentioned like this. And whenever you're going for the 2 power k by 2, if you want to solve this one, so again we are supposed to calculate 2 power k by 2 value. So that is t of 2 power k by 4 plus 1. In order to find out this one, again we can just simply we substituted there t of 2 power k by 4, and it is a t of 2 power k by 8 plus 1, and so on. Fine. So I want to generalize this. T of 2 power k is equal to, so 2 power k in terms of 2 power 2 power k by 2, 2 power k by 2 instead of 2 power k by 4, 2 power k by 4, it is in terms of 2 power k by 8, and so on. So when you consider this one, t of 2 power k by 2, so 4, you can also write this one as a 2 square, 8 2 cube. So when you substitute the thing, this one 2 power k by 2 plus 1, so simply 1 plus 1 is a 2, and again t of 2 power k by 2 cube plus 3. So in order to generalize this one, 2 power k in terms of 2 power k by 2 square, 2 power k by 2 cube, the constant, we can see that it is 2 because it is a square. The constant here, it is 3 because it is a cube, likewise. So if you go on like that, finally already k that we are already used there. Now let us come to the place where you are going to find out 2 power k in terms of, again we are going to generalize this one. If at all it is t of k by 2 power L, if it is something like k by 2 power L, then automatically when 2 cube is there is 3, 2 square is there, it is 2, 2 power 4 is, if it is there, it is 4, 2 power L is there, it should be L itself. So that's the thing that we need to understand. And here t of 2 power k by 2 power L, if k is equal to 2 power L. What is going to happen? K by 2 power L is going to be a constant, no? So 2 power n. So how we are going to write this one? That is equal to T of 2 power k by 2 power L. L is equal to 2 power L. 2 power L by 2 power L, that is 2 power 1. That is T of 2. And coming to the here, the part L part is there that we are supposed to find out. So how you are going to find out the L? When you apply the logarithm on both sides, we are going to find out the value of L. From here, we can say that L is equal to log k to the base 2. Log k to the base 2. So this is about T of 2 is equal 2 plus log k to the base 2. And in the previous algorithm, when consider this algorithm in the previous slide, we mentioned that T of n is equal to 1 if n less than or equal to 2. So when is equal to 2 also, it is the value is mentioning that that's value is 1. So that is, this is 1 itself plus log k to the base 2. Actually, k also we have considered this one also here. So yeah, n is equal to 2 power k. If n is equal to 2 power k, we started this one in the place of n, we mentioned that 2 power k. Likewise, it is get started, and finally we came to the place where we are mentioning the 2 power L here in the 2 power k by 2 power L that we have considered, and finally we come to the place that 1 plus 2 log of k, and this k has to, again it should be come back to the form of n itself. So n is equal to 2 power k. If I want to find out the value of k, if I apply the logarithm on both sides, log n is equal to log 2 power k. So automatically k comes. So k is equal to log n by log 2. That is nothing but k is equal to log n base 2. So here, this is equal to 1 plus log of log n base 2. Because here the k is equal to log n to the base 2. So we have to consider this part. Please listen carefully. Don't worry about these kind of things. So all the time we are going to get the same answer for this kind of problems. Only the thing that we have to understand regarding this recursive algorithm is a of n, if n greater than 2, then return a of square root of n, else 1. So here the two things that we have to take into consideration. We generated a recurrence relation, and afterwards we are trying to resolve it by considering that n is equal to 2 power k like this, and finally we came to the one place where we are going to solve the problem again k, and by taking the 2 power L. So this is simplified, and at one level we solve this problem. And coming to the next level, finally we are going to solve the problem k is equal to log n to the base 2. Here the k is the log n to the base 2. Now the step count, we can also mention this one as a step count also. 1 plus log of log n, right? So if it is a 2 power n, 2 power 10 is there. So 2 power 20 is there, right? So the numbers are there that we are going to consider here, and so this is a constant. If the log of log n, if n is a bigger values, so finally what will be the time complexity of this one is order of log n. So for this kind of algorithms. We are supposed to generate a recurrence relation. From that recurrence relations, we are going to get a time complexity. So in the beginning, we have seen that time complexity we can do it in the two ways. That is finding out the total step count, or with the help of the recurrence relation also we can do that, right? Now let me give one algorithm. You can also try. So what is the time complexity, or what is the space complexity of this algorithm, right? Definitely all of you can do it easily. Algorithm. So our algorithm is a recursive algorithm, that is a factorial itself. So let me say the fact n, and here if n is equal to 0, then return 1, else